Alright, welcome back. This is the last video we're going to be covering for section 2.2, and we're going to talk about the washer method, which is similar to the disk method we looked at in the last two videos. Except here, when we go to rotate our representative rectangle about the x-axis or the y-axis, this figure 2.22 here shows an example of rotating about the x-axis, and when we do that, you'll notice that the representative rectangle doesn't touch the x-axis. So when you rotate, there is a hole in the middle of this. It kind of looks like a washer. If you're familiar with nuts and bolts and stuff, a washer is something that goes around a bolt. And so that's going to change what our object looks like. It won't be completely solid anymore. It'll have a hole going through it. If you think about adding up all those washers from, in this case, it looks like this picture, this area goes from 1 to 4. So if you add up all those washers from x equals 1 to x equals 4, you get this solid over here that you see in part D of the figure. And so the formula changes. Instead of v being the integral of pi times the radius squared dx, in this case you have to kind of think about it as, okay, we got this disk and it has a radius of r, but it's got this hole in the middle. And so if you actually thought about it as two disks, a disk with a big radius, say r, and then let me change colors here. And then we have a little radius in green here. Let's call that little r. Then our volume could be thought of as subtracting the volume of that little small disk away from the volume of the big disk with radius r. And so our formula for the washer method looks like this. And what's different about this is, again, instead of it being pi r squared, it's pi times r squared minus r squared, or the radius of that big disk minus the radius of the smaller disk where the hole is. And so I actually like to rewrite this. I like to write it as the integral from a to b pi times big R squared minus little r squared dx. Of course, we can do this in terms of y as well, but we're going to think of this as our outer radius, or our bigger radius. That's our outer radius, and this is our inner radius. Of course, to see this worked out, we need to look at a graph and think about what the inner radius and the outer radius would be. So let's do that with example 3 here. Little note there, note the outer radius is the distance from the x-axis of revolution to the outer curve, the curve farthest away from the axis of rotation. And the inner radius, that was big R, the inner radius, little r, is the distance from the axis of revolution to the inner curve. So if we look up here in figure 2.22 again, this distance here would be big R, and this distance here would be little r. Okay, so let's sketch the region here for example 3. It says, sketch the region bounded by the given curves. Draw a representative rectangle to find the volume of the solid rotated or obtained by rotating the region about the specified line. The region is bounded by y equals square root x and y equals x squared, and we're rotating about the x-axis. All right, so let's draw this in here. Okay, we have y equals x squared. Y equals x squared is a simple parabola. Goes through the point 1, 1. Of course, it goes on this side as well. That doesn't look very symmetric. Let me redraw that over there. All right, and then we have y equals the square root of x, which goes the other way, right? There's y equals the square root of x. So this is y equals x squared. This is y equals the square root of x. We got our area there. And let's go ahead and put that representative rectangle in there like we always have. In this case, we could actually go about the we have to go about the x-axis. So we're rotating about the x-axis. So we need our disk to go that way. So the width there is dx. And so if we think about what this is going to look like if it actually rotates about the x-axis, our disk is going to look something like that. And then our smaller radius is going to be from about right there. And so the bigger radius, that's r, that's determined by the top curve, which is the square root of x. And the little radius is determined by, that's little r, that's determined by the bottom curve, which is y equals x squared. And so, using the disk method, or in the washer method, just like we talked about right up here above, remember, the volume is equal to the integral from a to b of pi times the big radius squared minus the little radius squared, or the outer radius squared minus the inner radius squared dx. And in this case, our x's are going from, if you think about that representative rectangle, it moves from 0 on the left to 1 on the right. So we're going to take the integral from 0 to 1. We have pi. We already said our outer radius is that top curve. That's the square root of x squared minus the inner radius, or the little r, which is x squared. Okay. And before we take the antiderivative, we can go ahead and simplify that. So move the pi out front. Square root of x squared is x. And x squared squared is x to the fourth. And taking the antiderivative, we get 1/2 x squared minus 1/5 x to the fifth. We're going to evaluate that between 0 and 1. We get pi times 1/2 minus 1/5, which is 3 pi over 10. And that is an example of the washer method. So there is one more example in this section. It's example 4, which shows the washer method for another problem. Actually looking at it, these are a little bit more complicated because we're not going to be rotating about an axis. Instead, we're going to be rotated about x equals 4 and y equals -1. And so I'm going to post the solutions to both of those problems for you to take a look at. Make sure you look through it and see if it makes sense to you. Ask me questions if you need help with understanding it, because you will have a problem in your lab assignment that deals with one of those more difficult ones. So that's all I got today. I'll see you in the next video. Thank you.